Okay, we're looking at the second year stats and mechanics textbook, and we're at exercise 8E, which is on integrating vectors. We're on question 8, so the last question of this exercise. So I am given the velocity in terms of t. I'm given the start position, and I'm asked to find an expression for the position in terms of t. Right, so no mention of integrating, but that's what I need to be able to recognise that the position vector, I'm blinding it twice, the position vector is going to be the integral of velocity. So 4t minus 3I plus 4j. Okay, so 4t is going to integrate to 4t squared over 2, so 2t squared. 3 is going to integrate to 3t. I'm going to do my constant of integration all together at the end. So when I look at my j vector, 4 is going to integrate to 4t, and then I mustn't forget the constant of integration. Okay, so it tells me that when t is 0, r is I plus 2j. Don't we need those brackets? So r is I plus 2j. So I plus 2j is, so if I sub 0 into that, so that's obviously 0. If I sub t 0 into that, it's 0. So that's my constant of integration. So I'm going to do this in a slightly long-winded way, so you might be able to cut out this step, but just to be really clear where I'm getting my final answer from. So that's what I already had. That's what's highlighted in pink. I've now got the value of my constant of integration vector. So the nicest way to give that as a final answer is going to be to have all of my I components together. So 2t squared minus 3t plus 1i, and then all of my j components together. So plus 4t plus 2j. Okay, and that's a position. So that's going to be in meters. And I'm just going to check that answer. Yeah, we're good. Okay, so onwards and upwards. Right. So then we've got a second particle q. So as soon as they start talking about a second particle even, that worries me a little bit in that I don't want to get mixed up. So I'm just going to add a subscript p there. So that's my position of p. Okay, so we've got the velocity, and it's a constant velocity. So and then I'm given the start position. Right. So if it's constant velocity, its displacement is just going to be velocity times time. So for q, so the position of q is actually just going to be its initial position, so r0, plus its velocity times time. Okay, so that's because it tells me it's a constant velocity. Okay, so the position of q is going to be its start position, so 11i plus 5j, so that's its start position, plus its velocity, which I'm given there, times time. So that's just going to be 5i plus kj times time. Okay, so that did come up in the first year part of the mechanics course. Okay, so just to reiterate what we're saying there, if you need the position of something, you basically want its start position plus how far it's travelled, or the displacement that it's travelled. Okay, all right, so I'm going to tidy that up. So the position vector of q, so again, I'm just going to get all my I and j vectors together. So in terms of I, I've got 11i plus 5t I, and then in terms of j, I've got 5j plus kt j. Okay, and I'm told that they collide, so there is going to be a point where they are in the same position. So they are going to collide when their I vectors are the same. So 2t squared minus 3t plus 1 equals 11 plus 5t. And it's going to leave a bit of space, I'm going to do a bit more working there. But then, so if they do collide, they need to be at the same I position vector and at the same j position vector. Okay, so the reason I've left myself a little bit of space is I can actually just solve this equation to find t, and because I know that they collide, I can then use that value of t in this equation to find k. So I'm just solving a quadratic here, so let's make it all equal 0. Let's cancel 3 by 2. I've just about left myself enough space, so t minus 5 and t plus 1. So t is 5, t is minus 1 is a solution, but obviously not valid in this case. So they collide when t is 5 because they're not asking do they collide, they've told me that they do. So at 5 seconds, that's when they're at the same I position vector. So they must also be at the same j position vector. So I'm going to use t is 5 in this, and that will let me find k. So if t is 5, that left-hand side is 22, that right-hand side is 5 plus 5k, so 17 is 5k, so k is 17 over 5. Okay, let's just double check that. 17 over 5, yep, that is the same as 3.4. Okay, so find the position of where they collide. Well, to be honest, if we've got, if you've answered B part 1, so I should have labelled it, that's part 1, then B part 2 is much more straightforward. So it's a bit all or nothing, this question, I think. So we're saying they collide when k is 17 over 5. So it should be that I can either use RQ or RP. So I'm saying they collide, they should be at the same point then. So let's use RP. In fact, no, I'll tell you what, let's use RQ just so I can see it on the same screen. But we could obviously check both as well. So I'm going to use that. So I'm looking when t is 5, and I'm saying that k is 17 over 5. So using those values, the position of q is going to be 11 plus, so if t is 5, that's going to be 11 plus 25, so 36i. And k is 17 over 5, and t is 5, that's just going to be 17. Oh, sorry, I missed a plus from that. Plus, so I'll double check this, I think I get 22j. Okay, so that would be my answer. And certainly, if I was in an exam, I would then be just double checking that. So even if I don't write it down, let's go back up. So I would just be double checking on my calculator even, that when I substitute t is 5 into this, I get the same answer. Well, I'm going to get 22, yeah, which we did get for j, so that is going to give me 22j. And I'll just stick that into my calculator. So 2 times 25 minus 3 times 5 plus 1. That gives me 36. Yeah. So that's just double checking. And then there's a third check. Obviously, you can't do this in an exam, but we can have a look in the textbook. Yeah, we're good.